from the University of Strathclyde, which is based a bit up north in Glasgow, Scotland. So first of all, I'd like to really thank the Grakn team for inviting me to share a bit about my research. It's really exciting to be here at the first Grakn conference. And this morning we've seen a lot of very exciting applications, so related to cybersecurity, taxes, biomedical. And for this application, we're going to increase a bit your altitude, and we're going to get to, hopefully, low Earth orbit, right? So as you can imagine, designing a spacecraft, designing such a complex system is not a simple task, especially in the forgiving environment that is outer space, right? So if you forget to tighten a bolt, or if you build your equipment, for instance, an accelerometer upside down, which actually, by the way, happened to a NASA mission, I think in the 70s, and it did not go well at re-entry, trust me. Well, if you don't develop your product thoroughly and with great care, well, it's going to be quite impossible to go out there and fix it. Between us, I think, of course, in a couple of years, we're going to see autonomous robots, spacecraft, which are going to be able to go on orbit and perform maintenance, but we are a bit, I'm diverging, and this is, in the future. So all I want to say is that in space, we have very little or no margin for error, and maybe this explains why we have sometimes a bit too much documentation. There's actually absolutely nothing wrong with this spacecraft, don't worry. This is Sentinel-5P. P stands for precursor. This is a mission that was designed for the European Space Agency, ESA, and it was launched in October 2017 in low Earth orbit, and it's helping us monitor the air quality, so helping us understand the concentration of some pollution into the atmosphere to help monitor, for instance, climate change and also protect our health. This is, for instance, a product that was generated with Sentinel-5P data over, I think, from April to September 2018. So the concentration you see here is nitrogen dioxide, which is usually produced by, I believe, traffic or for industries, by industries related to the use of carbon fuel. Just as a little, just so we hear, yeah, in this highly concentrated area, and I don't know if people from TNO are around still, and as a little advertisement, so as you see here, like here in Scotland, our air is absolutely clear and perfect. This is a little advertisement for Scotland. There's only one in this presentation, I reassure you. All right, so as any spacecraft, Sentinel-5P must have gone through the same classical kind of development step for a spacecraft. So it starts here in the feasibility study, phase 0. So you usually have a scientist that comes to see the, let's say, the space system engineer, and they want to monitor, for instance, deforestation in tropical areas. They want to observe all the boreal forest above latitude 60 degrees, or they want to go to Europa and check out if there is water and life. So in the feasibility study part, basically we're trying to establish quickly if, well, you have guessed it, the mission is feasible. Feasible economically, technically, and in some cases within a defined time frame. So if the mission has a go or no go, well, if it has a go, it will go into phase A, which is a proper feasibility study, which lasts 1 year usually. Then you will see a more kind of defined design appear in phase B, and in phase C, you will have a detailed design. In phase D, you have all the production, qualification, testing, very important for us. And in phase E, you have a quite exciting part, usually for the general public, which is the launch, the big firework, and then you have utilization. And now we've added, since a couple of years, the disposal, which is basically you have to get rid of your spacecraft. You can just leave it in orbit. It's just, we have a problem with space debris, basically. So so in this talk, I'm just going to focus on the feasibility study. So you want to assess as fast as possible whether your mission is feasible, right? Otherwise, if not, you want to move on quickly. So one way to converge as fast as possible towards a sound design is to use concurrent engineering. Basically, in concurrent design, you put all the experts you need to design a spacecraft. So in general, in the middle, you have kind of the orchestra master. You have the system engineer, then you have engineer in charge of thermal subsystem, structure, propulsion, mechanism, etc. So what you do is you simply lock them in a room for a couple of hours, for a couple of days together, and they are designing their subsystem at the same time, right? So in parallel. So whenever, for instance, imagine the shield guys, we're going to sign, for instance, so we're going to have a lot of radiations, right? So we need to increase the shielding, so they will let know as soon as possible the structure guy, and then you'll need to let know the propulsion guy who might need to change the .v because the inertial movement of a spacecraft will have changed. Anyway, so this is a way to really converge as fast as possible towards a sound design, as I said. And actually at the Strathclyde University, we have such facility. We call it the CCDS, the Collaborative and Concurrent Design Facility. And the slightly more fancy room here is the Concurrent Design Facility, so the original one at the European Space Agency. Right. So usually this kind of feasibility studies, they are divided in 3 main steps. So you have the preparation step. So this is where the system engineer and the client, so imagine the scientists, they come together, they define the first mission requirement, trying to get the mission drivers. And in this part, they really heavily rely on knowledge reuse, meaning they're going to go back to previous similar mission and try to find system architecture which have been validated in the past or which are known to be working. And they're trying to estimate as well as possible the input parameters that they will give to their colleagues, to the subsystems engineers, so that we'll be able to converge faster. So keep that in mind. So in the study, this is when you have all the engineers in the same room, right? So they're generating new simulation, mission analysis, thermals, models. We also have engineering models, and we are still relying a lot on Excel and PowerPoints. And the output is basically this final report and also the engineering model. So I'm showing you this slide also to kind of try to make you understand that this is a process that is still very heavily document-based. So we're trying to move towards model-based system engineering, but as you can see, we're still generating a lot of unstructured data, right? So report, PDF, PowerPoints, etc. And now imagine that I guess I have to stop showing this to the screen. So now imagine that they've done that for all this mission over the past 20 years of the existence of ESA CDF. So every round, every dot is a mission, and then the bands is basically the different kind of mission. So this is Earth, orbit, etc. Right, so, and this is just the tip of the iceberg of unstructured data that we have to deal with in the field of space mission design, right? We also have publications, equipment data sheets, all over textbooks. This is all the unstructured data. And we have, in addition, structured and semi-structured data, so engineering model, online databases, and simulations. Usually, actually, in my work, I focus more on applying NLP to unstructured data. So we're doing topic modeling, applying Word2Vec, and so on to these reports. So right, so I just want you to get the message that we have a lot of accumulated unstructured data in the field of space mission design, which maybe sometimes explain why our engineers may feel like this when it comes to search for any information. And at the start of my PhD, I tried to estimate how much time were these people spending looking for information. And the result was a bit higher than I thought, actually, initially. So some people were spending maybe up to half of their time actually looking for information. We did this survey with 47 experts from the European Space Agency who are involved in these feasibility studies, like I was saying. Right, so this clearly showed us that there is a kind of information retrieval bottleneck at the early stages of space mission design, and also reassured me that maybe my PhD had a sense and a meaning. So our approach at the University of Strathclyde was to start developing an expert system, so a program that is able to encompass the knowledge of expert and mimic expert reasoning, right? So we wanted to support decision-making at the early stages of space mission design. and to valorize basically knowledge reuse. And the reason I'm here is also because we wanted to develop the expert system knowledge base relying on Grakn. So we've been working on this since January 2018 in partnership, as you can see, with the European Space Agency, REA, Airbus, and SatSearch. Right. Just want to show you an example of what an expert system in the field of space can look like. So this is Simon. Simon is obviously on the right on this image. It stands for Crew Interactive Mobile Companion. It has been developed by German Space Agency, DLR, in cooperation with Airbus, IBM, and LMU. So the reason why we're developing expert system for astronauts is just simply that when we're going to go to the moon, to live on the moon, we're going to have a delay communication of back and forth of around 4 seconds. So that's manageable in a conversation, right? Maybe slightly annoying. But when we're going to go to Mars, we're going to have a communication delay between 8 and 44 minutes. And that can quickly become annoying in a conversation. And especially if you are in an emergency situation and you need an answer quickly, right? So one of the ideas is that to replace the on-ground support, we could instead have these little robots, so the expert system like Simon, who are going to become the technical assistant of the astronauts. And Simon can also do a bit more. So it's going to be a bit noisy because we're on board the International Space Station.
Simon, play my favorite song.
Ah.
Yay, I like your favorite hits too.
I don't know if you can hear that. Ouais. So basically, the astronaut, Alexander Gast, is asking Simon to play his favorite music, and Simon is like, yeah, I'll do that, no problem, and starts to play an unknown music that I have no idea, but apparently it's Alexander Gast's favorite. Right. Actually, for a little story, this is Simon 1, which was sent to the ISS in September 2018, and last December, the team developed Simon 2, which was sent to the ISS last December, and it's been improved with tone analyzer by IBM. So now it's kind of capable to assess the emotion of the astronaut, which is going to be also important because movers and technical assistants, when you're going to be traveling to Mars, which is by the way a 7-month trip one way, we also need to assess the psychological state of the astronaut. As you can imagine, that's pretty much a long trip far, far away from home. Right, so I was a bit diverging. I'm going to go back to the early stages of space mission design. So one of the first applications we did with Grakn was trying to migrate a structured database into a Grakn knowledge graph. So we took the CEOS database. CEOS stands for Committee on Earth Observation Satellite Database. It's basically a very complete database that encompasses a lot of information about a lot of Earth observation missions. So I simply took from their website their table, which I migrated into just a simple JSON file. So here you have this example of a mission with an ID, with its name, and basically all that it can do, the agency it's related to, if it's what kind of orbit it's on, if a mission is still active, and so on. So in the middle of Python script, I basically migrated it to this very simple Grakn knowledge graph, knowledge base. So in the middle you have the entity of a mission, which is, we decided to make it more exciting to relate it to a mission status, whether it's active or not, orbit type, mission agency, and here you have all the different parameters. So end of life, when it's supposed to be, to stop being active, mission name, well, basically everything you need to know about the mission. And then this has been quite useful for us because, of course, one of the first things when you would be developing, as I say, a new mission is that you're looking for similar missions. So it can be very useful to very quickly assess which other mission is on the same orbit, which other mission has the same kind of goal, the same kind of instrument, optical, radar, and so on. This is just to show you like an example of one spacecraft, which is a Pléiade 1B. It's a French spacecraft owned by the CNES, the French Space Agency. And honestly mostly used for defense and observation with a very high resolution camera. Yeah, so it just shows you maybe the content, and now you can imagine what querying can do to kind of connect it and provide more analytics on the content of this database. And examples that I want to go more into details, this is information retrieval from the engineering model. So if you remember, I said that during these studies, we were creating this engineering model, which are representing the spacecraft. So last May, a team of 13 very brilliant PhDs from the University of Strathclyde, yeah, I'm in the middle, this is kind of all my colleagues, we decided to get on the challenge. We started a challenge that is called the Strathclyde Concurrent Engineering Challenge, basically. So we wanted to design a nanosatellite, so it's even smaller than a CubeSat, for instance, a very small spacecraft, which would perform flybys of near-Earth objects, so basically asteroids. And we wanted to design it from scratch in basically just a week. But we just spent the whole week locked in a room designing it. So the output was NIACOR, which stands for Nanospacecraft Exploration of Asteroid by Collision and Flyby Reconnaissance. So we actually published our results in a paper if you're interested. This is the link. And this is just a bit of a patchwork of all the different models and figures we've done during this week. So you have a thermal model here, very fancy mission analysis trajectories, how you want to store the payload in the fairing of your rocket, and basically the configuration of a massive antenna, because we're so far from Earth and you need to send back data. Right, so, apologize. Yeah, so we also created this engineering model, so you can't really see, but here on the right there's a product tree, so you have all the equipment per subsystem. And here on the left, you have the requirements, which are really your mission driver and the thing you really have to keep in mind when you're designing your spacecraft, that you have to fulfill all the requirements. We generated this engineering model with a CDP4, which is a software provided by REA, our industrial partner. Right, and basically the structure of this engineering model is dictated by the ECSS, ETM 1025A, which is basically a standard by the ECSS, which means European Cooperation for Space Standardization. And it's, this standard, allows to share the models in between the different agencies and industries that are involved into concurrent design. So this is the migration of this this standard into Grakn. So at first I was really impressed by my number of entities, attributes, and relationship, but after seeing the biomedical graph, I'm sorry, this is not so impressive. But basically this was not given to me as a Grakn, in the Grakn format, obviously. I was given a UML model by the European Space Agency, and I had to migrate. First, I had to understand UML model because I had no experience in it. My background is just in aerospace engineering. So I had to migrate to understand, to establish kind of a bridge in between the concept of a UML model and the concept in GraphQL, right? So the entities name, the data type, the relationship were especially tricky because they would not necessarily transfer to relationship. For instance, the inheritance relation was actually described in Grakn by the sub, right? Entity 2, sub, entity 1, and inherits the properties of entity 1. And yeah, or simple property just were actually referencing to a value tab, bool value, so it would become a simple attribute. It was also quite useful that Grakn allows to modelize abstract entities because we had some in the UML model. So this is just also another example with non-UML. Of course, this is the kind of one of the classes in the user manual. So this is a person. The person is a thing. The thing was just the top category. So just to show you, so this is the attribute. So for instance, a person has exactly one given name. Well, that would become an attribute of the entity person in GraphQL. Or then you had also the composite relationship that we define as roles in relationships, right? We differentiate containment relationship, composite relationship and non-composite relationship. In a composite relationship, if one of the elements of a relationship is removed, then the other element is as well, I mean the one which is being targeted. Right, so yeah, this was fun. So I spent 4 months at RIA, my industrial partner, basically doing this. And then we could it was worth it because then we could very easily migrate an engineering model. So in this case, the NIACOR model, right? So the student engineering models that we did last May, we could migrate it into Grakn. So here, for instance, well, you can't really see for sure. This is the spacecraft, NIACOR in the center, and these are all the different subsystems which are related to this spacecraft, right? So if we want to take a closer look, this is the payload subsystem. So as you can see, we had a camera, we had the LiDAR, the spectrometer. This is still at the early stages, obviously, so if you were at a later design phases, you would have much more equipment and much more detail. Although, I mean, you can go inside of these entities and check out there is more content. This is the thermal subsystem, so we have the heaters, the MLI, the multi-layer insulation. This is kind of a golden cover that you see on the outside of spacecraft usually, and radiators. And one more, the AOCS, Attitude and Orbital Control System. This is the system that allows you to control the attitude and the positioning of your spacecraft on orbit. So here again, many different equipment, the star trackers, reaction wheels, the propellant. I'm sorry to throw a lot of equipment at your face like this. Yeah, and something really important also in the design of spacecraft is handling requirements. Requirements, they are often way more than this. Really hard sometimes to keep track of, the evolution of your requirement, to make sure you've satisfied all the requirements. So at least with this, with Grakn, you can have a much more comprehensive overview of your requirements and have a better, just better traverse like the status of your requirements. So I think my last example, is the flight dynamics requirements, when you can check out also the contents of the requirements. Right. So in conclusion, I wanted to say that I think so. My background, as you know, is more in aerospace engineering, so it's not in software engineering. But I think that Grakn had a great advantage. It was quite easy to pick up. As Aika was saying, it's quite high level, so I think anybody can learn and use GraphQL. Also, I think we're still at the beginning of what we want to do with Grakn. We want to implement it during a live concurrent engineering session to really more support actively decision making, because my example was like done after the concurrent design session. So now we want to do it really live, which is going to be a bigger step, and make it a kind of an active involvement in the design. And finally, if I convince my industrial partner of the European Space Agency to give me access to more engineering model, we can feed them to, we can migrate them to this knowledge graph and provide more analytics and more querying. So get more, like really be able to compare the different engineering model and the different design. And finally, so if you remember my initial, the bigger view, so the overall project is to prepare this design engineering assistant, DEA, the expert system we're working on. So this whole is to kind of create the DA knowledge base. And this is mostly, the work I just presented was mostly done on this structured data, but I'm also glad to talk to you about what we did on the unstructured data, so all the topic modeling, word2vec, and I'll be interested to discuss if some people are also doing BERT, because this is going to be also one of our next steps. Right, thank you for your attention. Do you have any questions?